Welcome to a lesson with Dr. Powell. Let's take a look at computing the derivative function for a polynomial function using a limit and synthetic division. All right, so we're computing the slope of the tangent line of this function at just the point x, where the point is at when x is just arbitrary. So we think of a point x, and the y value there is, well, we just plug x into the function, we get this. So we're finding the slope of the tangent line of this function at this point. Let's think about a point nearby where x value, we'll just call it a, and we're going to keep this x value fixed because we want to find the tangent of the slope of the tangent line at this fixed point where x is assumed to be fixed right now. And then, but a is going to be variable, and it's going to be moving in close to x. All right, we plug a in, and we just get the version of the function with a plugged in. Okay, and we look at the slope of the line segment between these 2 points, difference of y's over difference of x's. 3a to the 4th minus a squared plus a all over, well, then subtract off, of course, subtract this guy right here, minus 3x to the 4th plus x squared minus x. So subtract the 2 y values, and then subtract the 2 x values, so rise over run. And this expression right here, we're going to be taking a look at what happens, this expression gets close to as a approaches x. Now, of course, we can't plug in a is equal to x here because that's not defined. We're thinking of a as being the variable. That's the variable. And let's see. A is the variable. And x is considered as a constant here. All right. Okay. So a is changing. All right. Now, in particular, we can think of this as a polynomial, as the top is a polynomial with a variable a, and x is a constant. So really, when we look at this, this is like plus all of this stuff, where there's a plus in between there. To emphasize that, I'll just come over here and rewrite this as plus a plus. So this is a constant. Here, the x as well is a constant, and a is the variable. But this part, if you watch the video that I had that looks just like this, but I had an x equals 1 here because we're finding the slope of the tangent line at a specific point, it's really the exact same process, but this is a constant, and that's a constant, and we're going to do a division. The top actually will go to 0, and the bottom goes to 0. So a minus x is actually a factor of the top if it were to be factored. But maybe we don't know exactly how to factor it, but we can do synthetic division. All right? So we're dividing by a minus x, thinking of a as the variable, x is the constant. Change the sign of that, so we're going to have an x out here. Think about what's happening with coefficients of powers of a. Coefficient of a to the 4th is 3. A cubed, that's 0. A squared, it's -1. A, it's 1. And the constant term, just write that out. Actually, we won't even need it, but I'll just put it here anyway, just so you can see it. All right, and then the remainder slot, because really, this should be 0 in the end, and we're only interested in what happens right here. Okay, so we drop the 3, multiply by x, 3x, add, multiply again, 3x squared, add, we get 3x squared minus 1. All right, then multiply x times that, we get 3x cubed minus x. Is that right? Yes. So because I multiply by that, and then if I have done this correctly, let's see, 3x squared minus 1. Did I write that down? Oh yeah, because I changed signs. Okay, just making sure, double checking. Okay, and yeah, this looks good. Okay, then right here, I add right here. And maybe let me just make this a little shorter. Okay, so if I add that down, I'm going to have 3x cubed minus x plus 1. Okay, now you can double check. If you multiply x times this, you're going to get 3x to the fourth minus x squared plus x. And notice as you add, you will get 0. But really, we can stop right here and think about what this is in powers of a. So we can think 3a, so this is constant a squared, a cubed. 3a cubed plus 3x is the coefficient right here of a squared, plus 3x squared minus 1a plus 3x cubed minus x plus 1. All right, now what we've just done is we've taken this expression and rewritten it like this. Notice we don't have a domain problem. We can actually stick x in for a here, and so then that's going to be f prime of x, the derivative function of this guy right here. So if we plug an x value into it, it'll give us the slope of the tangent line. So plugging x in for a, 3x cubed plus 3x times x squared plus 3x squared minus 1 times x plus 3x cubed minus x plus 1. And we get 3x cubed plus 3x cubed plus, stripping the x in, 3x cubed minus x plus 3x cubed, and then we had minus x plus 1. Collecting like terms, we end up getting 12x cubed, and we have negative 2x plus 1. And we've just computed the derivative using synthetic division. Now perhaps if you're familiar with derivative rules or something, you might think, well, why in the world did we do that? But this illustrates how the idea of limit, of just changing the domain so that, but keeping the expression algebraically equivalent and plugging in, works extremely well with just a synthetic division process for any polynomial function. So you can actually get to the formula for the derivative with just a synthetic division, and plugging in a as x at the end right there. Thanks for watching.